Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to look at what the rank of the matrix A tells us about the solution to the matrix equation AX equals B. So let's take a look. So this is what rank R of A tells about the solution to the matrix equation AX equals B. That's what we're going to look at today. How does this go? Well, let me show you. Let's start out with the matrix A equal, how about this? How about the first column is 1, 1, second one is 1, 2, and the third column, I'm going to just get the third column by adding the first two. So how about 2, 3? And then I'm going to solve AX equals B. And let's see what happens. So what do I have? I'm going to, now remember, I'm going to just start right with the augmented matrix. So I'm going to write 1, 1, 1, 2, 2, 3. And it's important here to include B, and you'll see why as we go. So we have a B1 and we have a B2. And let's find our solution. And how do we find our solution? We take the augmented matrix down to RREF, the reduced row echelon form of A. So here we go. Let's start with row 2, and we're going to subtract row 1. So let's see. This is going to give me the new matrix of 1, 1, 2, B1. So the first row stays the same. The second row, though, becomes a 1 minus 1 for 0. A 2 minus 1, that's 1. 3 minus 2, that's another 1. And here's the key. The key is then we also have a B2 minus a B1. Okay. And we have one last step to find our solution. We're almost to R. What we're missing at this point, though, is right here. We need that to be a 0, the 0 above each pivot. So remember, reduced row echelon form means that there's a 0 below and above all pivots of the matrix. So let's take row 1. That's what we're going to work on. We're going to subtract row 2 from it. Let's see what we get. That becomes a 1. So we had a 1 minus 0, a 1 minus 1, a 2 minus 1. That's a 1. And then we're going to have a B1 minus B2 minus B1. We could probably clean that up. And then our second row is 0, 1, 1. B2 minus B1. Now, what is important here? What is important? What is important is, let's take a look at this. We have two solutions here, or we have two parts to our solution. Remember that the complete solution, X complete, it's comprised of the particular solution plus a null solution, xn. Well, in this case, our particular solution, let's write out our solution. Let's write out our solution. So our solution says that we have, now what we do is, remember, we solve for pivot variables. So I have that x1 is equal to, let's see, if I have a b1, that's going to be at 2 b1s minus a b2 minus an x3. And my second solution is going to be that x2 is equal to a b2. All right, we'll keep, it doesn't matter. b2 minus b1, also minus an x3. So if I write my complete solution, well, what I get now is I break this up into the pieces with the b's and then the x's. And so I'm going to do this a little quicker. Now I get 2b1 minus b2. And I come up with a b2 minus b1 plus I have an x3 as my common component on the vector of minus 1, minus 1, which would be the same as 1, 1. It doesn't really matter. So there we go. But look at what we have. So for this complete solution, notice what we have. We have a particular solution plus we have a null solution. So let's look at the rank of the matrix. So the rank R equals 2. The number of rows, M, is 2. And the number of columns, N, equals 3. So let's compare all these and see what this tells us. First off, when R equals M, which in this case it does because 2 is equal to 2, this is called full row rank. Full row rank. So all of the rows have a pivot in them. Okay. Also, what kind of a solution do we get? We have ax equals b has a solution. It has a solution x particular. It has a solution x particular. And now let's talk about the columns. The columns tell us the other part. So, or the number of columns. And that is, notice that the rank is less than the number of columns. In other words, 2 is less than 3. When that's the case, when the rank of the rows is less than the number of rows, then what do we have? Then we have x null. So for a problem like this, you could say that you could say the two key parts are that ax equals b has a solution, and we have a null solution. And as soon as you have a null solution, really that means it's an infinite number of solutions that are in part of the complete solution. Okay, let's take a look. I'm going to go down, and now let's try A transpose. Let's take a look at A transpose and see what that tells us. Well, A transpose is going to be a 1, 1, 2, 1, 2, 3. Okay. Now I could call this the matrix B, but it just seemed like a simple example to work with. So now what we're going to do is let's solve A transpose X equals B. Okay, so now I have 1, 1, 2, 1, 2, 3, and the augmented matrix is B1, B2, B3. Okay, and we proceed as you would expect. We start with row operations. I'm going to be so bold as to combine two. I'm going to start with row 2, and I'm going to subtract a row 1. And then I'm going to work on row 3 and subtract 2 row 1s. So if I do that, what do I get? That's going to be, the first row is the same. So I have 1, 1, B1. Then I'm going to have a 1 minus 1, that's 0. A 2 minus 1, that's a 1. And then I'm going to have a B2 minus B1. And then my last one's going to be a 2 minus 2 for 0. 3 minus 2 for 1, and then a B3 minus 2 B1s. Okay. Now we're not yet to the reduced row echelon form, so let's do that next. Let's take row 3, and we're going to subtract a row 2. So that's going to give me the matrix of 1, 1, B1, 0, 1, B2 minus B1. Sorry, I forgot which row I was on. Now we're working on the third row, so I have a 0. I have a 0. Then I have a B3 minus 2B1, and then I subtract whatever is in B2, which is B2 minus B1. That's my new augmented matrix. Okay, we'll clean that up here soon enough. One more step is to get to RREF. So then I'm going to take row 1 and let's subtract row 2. And so we do that. Well, what do we get here? We have a 1, a 0. Then we're going to have a B1 minus B2 minus B1. Then I'm going to have the second row is the same, 0, 1, B2 minus B1. And then the third row is 0, 0. Let's see if can we clean that up? I know I've got a B3, so let me write that. And then it looks like I have a minus 2 B1s plus a B1, so it's going to be a minus a B1. And then I'm going to have plus a B2. Wow, look at this problem. Okay, this is different. Let's see what we've got here. Now, the solution to this, the solution is, well, we can read it right off. The solution here is that x, the vector x, has components of x1 and x2. And the solution is, it's the first component, it's b1. Oh, so you have a b1 plus a b1, so let's write 2 b1s. Is 2 b1 minus b2. And then it's going to be b2 minus b1. Wow. So look at that. There is a solution. But also watch this. This last line says that 0 has to equal b3 minus b1 plus b2. Well, oops. Oh, b2 should be a minus. Oh, goodness. You shouldn't let me do that. I'm going to go fix that. B2 should be a minus. Let's put a minus there. Minus b2. So I need that, fix that here. Minus b2. And then, in other words, if I reorder these, this says that b3 has to equal b1 plus b2. All right, now let's look at our rank. So the rank are, again, we had 2 pivots, so the rank is 2. We have 3 rows. M is equal to 3. And n, we have 2 columns, so n is 2. Okay, let's start now with, we'll go in the same order as we did last time. So notice this. We have that r, which is equal to 2, is less than m, and m is 3. Wait a minute. So what happened here, though? Well, first off, ax equals b has, let's write it this way. Let's write it as possibly has a solution. What do we mean by that? We mean that ax equals b has exactly one solution, has a solution. So we'll put it this way, put colon. It's one solution, oops. It's one solution if the restriction is met, if the restriction, or how about this, even a better way to put it, if B is in the column space of, in this case we called it A transpose, of A transpose. Or, and if B is not in the column space, then b1 plus b2 won't be b3, and so we'd have or no solution. No solution. So that's what the rank tells us. And now this is called, now look at what else we have. Here we have that r equals 2. We have that r is equal to 2, but that's also equal to n. And so in this case, when we know we either have one solution or no solutions, this is when we have what's called full column rank. Full column rank. Okay. Well, there's two more cases here. Two more cases. The third case is if, let's just change A. I'm going to call it A prime. Say A prime, we get rid of that third column. So now I have 1, 1, 1, 2. Okay, 1, 1, 1, 2. Well, let's solve this. So if I have 1, 1, 1, 2, I'm going to solve the matrix equation B1, B2. So I should probably write that. That's what we're doing. Solve AX equals B, A prime X equals B. Well, what do I get? Well, my first operation is row 2 minus row 1. So now I have 1, 1, B1 in my first row. My second row becomes a 0. 2 minus 1 is 1. And I have a B2 minus a B1. And now to get to our reduced row echelon form, then I would need to take row 1 and subtract row 2. So that becomes my first row changes. Now I have 1, I have a 0, I have a B1 minus B2 minus B1, then a 0, a 1, and a B2 minus B1. Whoa, look at this. Look at this. So we can see our solution. Our solution is just right here. That's our solution. X1 is a 2b1 minus b2. Let's write that. So x equals 2b1 minus b2, and x2 is b2 minus b1. There it is. There's our solution. Well, what about that? That means I can solve, there's no restrictions because I don't have a 0 row. There's not an extra column, so I don't have a null space. So in this case, look at what we have. The rank in this is 2. The rows are 2, and the columns are 2. So when M equals N, right there we have a square matrix. And when you add that M equals N equals R, then we have a full rank matrix. Full rank matrix, which means that, which also means that AX equals B has one solution. Notice that there's no null space. So the null space in this case is just the 0 vector. So the null space is just the 0 vector. And in the complete solution then, the complete solution is whatever your one particular solution is plus your null solution. But that's just a complete solution of the particular plus 0. So your solution is just the particular solution. So we only have one solution when we have a full rank matrix. And also, it means some other things. It means that A prime is invertible. Invertible. And we've seen this in the sense that when we were trying to find the inverse of a matrix, we row reduced until the left side turned into the identity matrix. So we've seen that before. Okay, the third example The third example, I'm going to go up from yesterday, from our previous video's information, and I'm going to pick the matrix, I'm going to pick the solution, and let's see what happens there. Let's see what happens there. So I'm going all the way back up to the top of all of this work the other day. And what did I want? I wanted, let's just take this one right here. So I'm going to copy this. Copy, and let's go put this back down here where we can work with it. Oops. Okay, let's put that. Oops. Let's put it right there. Okay, there we are. I'm going to get rid of that little weird mark. And here we go. So notice this matrix. Let's take a look at this matrix. This matrix has M is 3, N is 4, and it has a rank. The rank is 2. Remember the number of pivots. It has a pivot. It has a pivot in the top left, and then you have to come down and over one, and there's the next pivot. But look at this. I have 2 columns, 2 extra columns without pivots, and I have a row of zeros. Let's see what those tell us. This row of zeros says that not all B are in the column space of whatever this matrix is. We'll call this RR because it's in RREF. Not all B. So there's possible restrictions. So you could get from this matrix equation, so solving, what do we call this? Solving Rx equals B may not have a solution. May not have a solution. Okay. But if it does, look at this. We have 2 free columns. I have 2 free columns. I have an x3 is going to be free and x4 is going to be free. So it may not have a solution, or it has infinite solutions. Infinite solutions has infinite solutions. And so in this case, x complete, if we have a particular, so this is an if we have a particular solution, then our x complete has a particular component and it has a null component. Okay? And so this is a case where we've added a restriction. And what do we have here? We don't have full row rank, we don't have row rank, we don't have full column rank, and we definitely don't have full rank. In this case, R is both less than M, the rank is less than the number of the rows, and the rank is less than the number of columns. And so what we see is either 0 solutions, or we see an infinite, I'm going to use the symbol, infinite number of solutions, meaning the null space, solutions plus the particular solution. And that is what the rank of the matrix tells us about the form of our particular of our complete solution. I hope that helps. Thanks for watching.